Notice that many of the rules that you remember from organic and general chemistry are still there, but they were like shortcuts. And they only existed because we were operating in a special limited conditions, right? With organic chemistry, what were we limited to? What was everything? Why is it called organic chemistry? Carbon, yeah. Everything was carbon and almost everything was periods what? Yeah, 1 and 2, right? We almost didn't touch anything on period 3, did we? Yeah, so organic chemistry almost completely ignores everything below period 2 and only exists on periods 1 and 2, right? And you know what? It works. It's probably 90-something% of compounds that humans worry about. So, whatever. But it's not all compounds, is it? You start working in solar, you start working in enzymes. Anybody know what enzymes look like? Okay, do enzymes function without metals? Does hemoglobin function without metals? No, and so we actually need to consider beyond organic chemistry, don't we? Okay, so if you remember your orbitals, so if we talk about molecular orbitals, then you have atomic orbitals from your atoms that are joining together to form compounds, right? Okay. And so what we're going to see is we'll have the atomic orbitals. They're going to join together, hybridize, to form molecular orbitals, okay? Okay. So we have several things going on. Everybody ready for it? Okay. So we have the atoms. They're going to take their atomic orbitals, and depending on the geometry that's most efficient, that's going to be lowest energy, most stable, right? They're going to hybridize. That's how we get things like tetrahedral. And so the hybridization for a tetrahedral is what hybridization? sp3. Trigonal planar? sp2, very good. And what's the linear usually? sp. But does it have to be sp? No. We can have direct overlap of S and S and P and P, etc., right? Okay, it just depends on if we have to add other stuff. Okay, so that's the hybridization, and that's what you're looking at right here in terms of a hybridization. Okay, and so we have carbon, for example. It's going to hybridize so that it can match up with the 4 hydrogens. This is going to be for methane, right? And so the 4 individual hydrogens, they each have 1 s orbital, don't they? And each of them has 1 electron in it. If we want to pair with those electrons, we have to have 1 electron per orbital, don't we? Okay? So this is not going to work, is it? If we tried to bond like this, what would happen is we'd have an s core, right? Which would be repelling the electrons around it. And then we'd have these p orbitals that would each be 90 degrees off each other, right? And they would match with 3 hydrogens, wouldn't they? And then we really couldn't make another bond. We'd have to do a coordination, wouldn't we, for this last s orbital here. Okay? And so that sounds nothing like the bonding you're familiar with, does it? That sounds crazy town, right? And so what happens is we have to hybridize first. So we hybridize by mixing the s and p orbitals together. We split out each of our electrons. This is typically called promotion, i.e. you're promoting an electron up into another orbital. Can everybody say okay? Okay, that takes up energy. So we're separating these electrons out so they can bond, right? And this is then going to hybridize, and what this is going to do is it's going to give you the most efficient arrangement of the 4 directions of electrons, right? Is that making sense so far? Okay. And hybridization has no energy cost. It's just the organizing the electrons into their most efficient distribution. Okay? So the hybridization, whenever you do a hybridization, it's always going to have the exact same energy. So if we were to take these orbitals, add these energies together here, these 3 are high, right? These are lower. And then we take the average, we're going to get these sp3 hybridized orbital energies. These are just the averages of these. Okay? Mm-hmm.
What's with the promotion saying it costs 406 joules? Is that
we have promoted electrons up into this.
So that's like pre-hybridization.
Exactly.
Basically. Okay, so that does take energy, but the
It
hybridization does not.
Nope, hybridization does not. Promotion does. Yeah. And this would be the same sort of thing that you would get from getting hit by light or any of that stuff. Those would also be promotions. Yeah. Okay. So we now have our hybridized electrons. Everybody okay with that so far? Okay. Okay. So the next step here is going to be, we're going to take those hybridized orbitals. They're then going to form bonds with the s orbital electrons and the hydrogens. Okay? Now, this is actually where you get your energy back. So bond formation always gives off energy, right? And you actually get your energy back. In this case, you get actually quite a bit of energy back. And you actually gain energy overall, right? And this is actually what determines if a reaction would happen and if you get methane from this. Okay? Okay. Is that making sense to everybody? Mm-hmm.
Can you explain hybridization just one more time?
Okay. So hybridization is going to have no energy difference. And it's just things arranging so that you fill out your orbitals. It's the recognition that what's really happening here is we're taking these orbitals, which are places for electrons, right? And instead of it being 90-degree p orbitals and then an inner shell s orbital, we're boosting them up so they're 4 different directions with 1 electron each, so we can form bonds.
Okay.
So the boosting it up out of that s orbital, that loses you energy, right? Yeah, you got to put energy into the system for that. This is just the rearrangement. We've already spent the energy.
Okay.
That making sense?
Yes.
Okay. Problem. And this actually always has to be true. The hybridization always has to be equal energy because it's just the rearrangement of those orbitals. Other way of saying that is we have conservation of energy, right? Because we're just taking these same orbitals in and putting the same orbitals out, we have to have conservation of energy. Okay? So we have 4 orbitals coming in. We have to have 4 orbitals coming out. We have to have the same energy coming in as going out, right? That making sense? Okay. Okay. So we form our bonds, and that's going to give us our wonderful CH4 that you know, your methane. Talking about smelling gas, right? Yeah, there you go. You must have been smelling this. Okay. Anybody have any questions there? All right. Fantastic. Okay. These would actually be the equations for those. So those would be the Schrodinger's equation. When we're actually looking at this, what we're looking at is wave functions overlapping in such a way that they bring harmony, okay? That they amplify each other, or another way of saying it is that they give an overall lower energy, okay? Okay, so think of it a bit like, anybody ever played the piano or guitar or something? Any music at all? Anybody? Do you guys know what like notes are? Harmony? Harmony? Everybody knows harmony? No? Apparently we need to do field trips and listen to music together. Okay. We're going to have to make a list. We need to meet on Saturday, okay? We'll listen to some music. We'll take a field trip. Okay. Okay. I'm serious. If you guys want, we'll meet on Saturday. We'll listen to music, take a field trip, and we can talk about harmony and stuff, okay? But so harmony is where you put together resonance between different notes, right? And so they have resonance, which gives them non-destructive interference that gives them constructive interference, right? Okay. And that's what you're looking at here. These are the sets of constructive interference, and these give you your Schrödinger's equations with these sp3 combinations. Can everybody see the sp3 combination? See that? No. So that's actually what the sp3 orbitals look like in terms of equation. Okay, this is what an sp3 orbital looks like, where it doesn't yet have anything else attached to the other side. Okay? So if you put something attached to the other side, this is going to pull these in. It won't be as broad, right? And you're going to get it right here, right? But this is before it attaches anything to the other side. And so this is your electron contour diagram. Again, the electron contours tell you where you're most likely to find those electrons, right? Okay, so you have your highest probabilities directly near these nodes right here. This is a node where you don't have any probability of finding it. And then this would be the other high probability area, right?
It's a SP3.
It's an sp3, yeah. And you have 4 of those that do the different directions, right? To make tetrahedral. Okay. Everybody sort of recognizing those? Okay. That's kind of what that looks like. Okay. So here we have the s orbital, the p orbitals. These are the sp3 and the normal orbital that you've seen in like organic chemistry. Remember, that's the 90% chance of finding the electrons within that. And they're pointed in the 3 typical tetrahedral direction, right? Okay. By the way, did anybody ever notice that, remember those rules I told you? Why is Z in this one? Lined up like that?
It's a tetrahedral. There's a
Yeah, so there's a C3, right? And so the highest rotation is the Z, right? So, like, back in general chemistry, we never told you any of this crap, and we just did it, and you're like, oh, that's the Z. But it had always been that way, right? You just never knew. Anyways. And so, yeah, we have our tetrahedral. That's the methane right there. The hydrogens are attached to those sp3 orbitals. And they're separated out like that because we did the promotion, and then the electrons had to separate so that they could pair with the electron from the hydrogen, right? Okay, is that kind of making sense so far? Okay, fantastic. All right, so let's talk about some of the traditional types of hybrid orbitals that form. This is going to be, again, a function of electron geometry. Really what we're looking at in these is this is how we accomplish those shapes, right? The electrons exist in electron orbitals. They're a recognition of the probability of finding an electron in that area, right? That's what an orbital is, okay? So by definition, separating the electrons out into their cardinal directions, that creates the hybridization, right? Okay, because the electron space is occupying is literally orbitals. Okay, so this one right here is linear, and you can have actually 2 different types of linear. You can have the SP, of course, and the SPZ is what you normally define it, because if you're linear, right, your highest rotational axis is Z. Okay, and so the P is always the Z in that one. This is trigonal planar, and that's going to be your SP2s, of course, and so that would be things like double bonds, right? And then those are going to be the px and py typically. sp3 is going to be your tetrahedral. This is your trigonal bipyramidal that has a d orbital that's going to get mixed in. And that's how you get the extended octet stuff, right? Okay. Note that the extended octet is kind of bullshit. And we'll talk about that. But it's like a simplification, but not really. It's kind of like a dodge around so you don't have to explain it in Gen Chem. Okay? All right. This is octahedral, and so we have a DT2 sp3 hybridization, and those would typically be the orbitals that you would mix in together. These would actually be the direct orbitals that are being used for those, by the way, in case you're ever wondering. By the way, note that, see these formulas down here? The dx2 minus y2? Does that look familiar? Anybody notice the quadratics on the character tables we just talked about? Guess what those are? Yeah, they're orbitals. See that? Doesn't it feel like we like undid the veil behind the curtains, as it were, of like general chemistry and organic chemistry? Okay, so this again is another hybridization, and here we have a linear, and everybody see that okay? Okay, and so this is sp, and we get 2 orbitals out, of course, because we put 2 orbitals in. Everybody okay with that so far? Okay. Okay. Again, these right here are the molecular orbitals or atomic orbitals at that point. Do you see another atom in either of these right here? No. So they are AOs, atomic orbitals, okay? They then would be combined with the s orbital from the hydrogen here, and then that would give you your molecular orbital, right? That would be the bonding part, okay? That's where we get that energy back. All right, so here's another example here. Again, this is that valence bond model. In this case, we have the water molecule. Again, that's going to be an sp3 hybridization. And that's dictated by the tetrahedral shape that needs to exist around the oxygen. And again, that's because we have 4 electron domains. Everybody's good with that? Remembers that okay? Okay, fantastic. Okay. And so we have our hybridization. 2 of those end up with lone pairs in them. 2 of them end up empty. And then that gives us our bond formations right there. Okay. Okay. All right, so let's go ahead and talk about some shapes here. So this is actually your formula where you have your hybridized orbitals and how much relationship the bond angle has with the decimal percent s character. So you would note, for example, when we're looking at water, for example, water does not have 109.5 degree bond angles, right? It has 104.5 degree angles. And what's happening there is the orbitals that have the electrons in them, just the electrons, lone pairs, are different, not symmetric, with the orbitals that are going to be attached to the hydrogens, right? So they're going to end up with different amounts of s character. And so if we go ahead and do this, note, I'm not going to talk about the d orbital character ones here. And I'm just not going to talk about that at all. It's just, if you need to do that and you're going to do that, then be in grad school. And you can learn it in grad school. It's just too complex. You would not want to work it out by hand. Okay. Okay. And so your experimental bond angle, HOH, is 104.5. If we plug it into this equation here, so this is the bond angle right there. We take the cosine of it, and then we solve for S, right? Okay.
What are you talking about, decimal percent S character? What is that?
So what this is, it's the percent of S character it would have. If this was perfectly sp3, for example,
Right.
so sp3 would have 1 out of 4 S character. Okay? So 1 divided by 4, or 25% S character.
Only one S will.
Exactly.
Okay.
So the overall for the entire molecule would have a 1 out of 4 S character, right? And 3/4 P character. Okay? For that oxygen. But in this case, those bonds are not the same, are they? Or I should say the angles are not the same. So you have lone pair sets and you have hydrogen on the other. Okay. So we go ahead and take our bond angle, we plug it in, we solve for S, and what we would see is that HOH bond angle right here tells us that those bonds are 0.2%, 20% S character. 0.2 S character. Okay. And so if we have these two OH bonds, they're going to have 20% S character. The remaining character would be P character, p orbital character. Okay. And the overall hybridization has to be sp3. And so what we would see is that the two lone pairs actually have to be the remaining S character of those. Okay. So, for example, we should have been 25%, right? We're 20% for the OH bonds. Everybody see that okay? Okay. Then that means that the lone pairs actually have to be 30% S character. They pick up the remaining 5%. Okay. Or another way of saying that is that we need to total to 100% for all four bonds. All four bonds have to split that total 100% S character, right? The entire S orbital. Okay? And so we have two bonds that are the OH bonds. Those are going to be 20% each. That's 40%, right? And the remaining two bonds have to be the remaining 30% each, or 60% total, right? And that accounts for 100% of the S character. Okay. Mm-hmm.
So that 30%, that applies to the lone pairs?
Yes.
Not the actual, like, on angles?
It applies to the lone pairs, that hybridization. So that hybrid orbital has 30% S character that has the lone pairs in it. Does that make more sense?
Yeah.
So it would have a slightly different shape than this OH hybrid orbital would. Okay? It would be more S-like,
Okay.
which is why it bulges out.
Okay. And you only multiply it by 2 because there's 2 separate lone pairs?
Exactly. Yeah. Yeah. So we have 4 bonds total.
Mm-hmm.
We have 2 of these types of bonds, 2 of these. Yeah. And because we have one S orbital, it has to total at 100%, the whole orbital, right?
Okay.
If we had 2 of them, it would be 200%, 3 of them, 300%. So our p orbitals, for example, we're going to have 3 of them.
Okay.
Yeah.
So you just multiply the 100 by how many
Yeah.
P orbitals?
Yep. We got to account for all 3 of those p orbitals 100%, right? Yeah. Okay. Okay, and so for example, if we look at that OH bond, right? It's more straight and narrow, isn't it? Right? It's going to be more contained. The lone pairs are going to be more spread out, right? Like a half S orbital. Okay? And so what we see is the lone pairs have higher S orbital character, which is why they're more spread out like that, closer to the oxygen, right? The hydrogen-oxygen bonds have more P character, so they're more jutted out like a P orbital would be. Okay? Is that making more sense? Remember that these literally are like the places electrons are going to exist so that they're excluded from each other, right? So, mathematically, these have to add up to be the places that exist around the molecule. Right? Okay. So if we look at the 70% P character, so our lone pairs would end up with 70% P character. Our OH bonds are going to have, the OH hybrid orbitals are going to have 80% P character, right? And so what we would see is 2 times 80 plus 2 times 70, and that's going to give us 160 plus 140, which gives 300 for 3 bonds, right? 3 orbitals. Mm-hmm.
I saw how it got the S character percents, but how does it get the lone pair?
It's just the remainder.
Okay, so
Yeah. So it's literally just the remainder. We know we have an S orbital that goes throughout this entire thing.
Mhm.
And so we've consumed 20% for 2 bonds. So the remaining has to be 60% divided by 2, right?
Oh, so that's where the 30.
Yeah.
And then
Or another way of saying it is it should have been 25%. This is 20%, meaning the remaining 2 have to be 25 plus 5%.
right.
The stuff that wasn't used.
That makes sense.
Does the relative math make sense to you guys, or the absolute math? Absolute math is this. Absolute? Okay. The 20 versus 25% didn't make sense? Okay. Okay. So I'll try to remember that. Relative math, no. Absolute math. Okay. So, anybody have any questions about that? Did I lose anybody? Did you guys catch that? Okay, fantastic. So the experimental bond angle for an H3, 107.2. Let's calculate the percent S character and percent P character in the three NH bonds and the lone pair of the N atom. What sort of hybridization are we looking at? SP3, right? Okay.
And we could figure out the hybridization by just looking at the ground state of each element pretty much.
Yeah, or you can just do the same thing we did before, back in Gen Chem and stuff, where we just take the number of electron domains, right? So in this case, you have 3 electron domains, 3 hydrogen bonds, those are 3 domains, and then a lone pair, 4th domain. Okay. Maximum separation for those, tetrahedral, sp3 hybridization. Yeah, they're directly related to the shape because it's what makes the shape, right?
I can't use the ground state though, right? Is that?
Yeah, you could draw a ground state. It's just going to take a while.
Well, I mean, if I know that, you know, nitrogen is in the p orbital and has a 2s and 2p3.
Oh, what do you mean by ground state?
What I just said, like the orbitals, like I know that nitrogen has an s and a p orbital.
Oh, you're talking about electron configurations.
Yeah.
Okay. Okay, there are actually 4 ground states in this. Than what we're talking about right now. That's why I was like, okay, I had thought you were talking about drawing out the orbital ground states for each of the promotion. Yeah, it's going to be the ground state for all these, unless you specifically had talked about. That's what the promotion is, actually. It's boosting it up from the ground state. Yeah. Okay, folks, everybody ready? No? Oh. Uh-oh. Admittedly, I don't have my calculator. What's the cosine of 107.2?
I got -0.2957.
That's fine. Okay. I mean, it shouldn't matter because everything's multiplied, right? By that number. So you'll just end up with a flip sign. Did you all get the same answer, by the way? Cosine of 107.2? Okay, good. I'm double checking because there's 2 modes you could be in, right? Degrees versus, yeah. And sometimes these damn calculators. Yeah. Okay, folks, I'm going to go ahead and start going on. Is everybody able to solve this formula okay? Okay, take a cosine of the 107.2, right? Okay, and then you're going to multiply this over, and so you'll have 107, what was it again?
The negative 0.29.
0.29? Okay. I'm just going to skip the negative because it doesn't matter.
Yeah.
Like, it just flipped the sign for everything, right?
Mm-hmm.
Okay, so 0.29. Okay. 0.29 times s minus 0.29, and then it'd just be s over on the other side, right? Okay. And so then you'll subtract over s, divide it over, and that's going to give you your answer. Yeah. And it's fine that's negative, because what you'll notice is you'll end up with a negative number, then plus, then divide by, and again, it doesn't matter what the sign is. Okay. And so the answer you should have ended up with 23% S character. So if it's 23% S character, how much P character does it have to have? The remainder out of 100%, right? So 77%. So that's going to be your 3 NH bonds. So if we want to find out the other one, the easiest way to do that is going to be take your 3 bonds times their S character, and then subtract that off 100%, right? So you got 3 times 23.3, that's going to give you 69%. Subtract it off 100%, and that's going to give you 31% S character for the lone pair, and 69% P character. Now, a little double check whenever you do these. S character pulls in towards the nucleus, right? P character juts out, like you usually associate with most bonds. Okay? And so lone pairs tend to have more S character. Bonds tend to have more P character. Okay? Okay. Anybody have any questions there? No? All right. Fantastic. Okay, so your experimental bond angle for H2S is going to be 91.1 degrees. Does that sound very tetrahedral to you? That really doesn't, does it? Because it is not. That is not tetrahedral, is it? Its S character would only be 0.035. That is basically almost no S character at all, right? And so shouldn't this be analogous to water? Shouldn't it? Right? It's in the same period, right? Look at that. It's the same group. Should be kind of like water, right? H2S, H2O. Yet it's not, is it? Okay. If it's giving you 90-degree separations, and that's the degree angle between p orbitals, isn't it? And so what does that tell you about this? These are essentially unhybridized orbitals, aren't they? You have p orbitals making bonds. Okay? And so one of the things that you can do is, again, in this H2S, what we can see is that the atomic orbitals, they don't need to hybridize. That doesn't explain our observed geometry, does it? And they can... Why do atomic orbitals hybridize? I mean, that promotion step costs energy, doesn't it? So why do they hybridize?
Because overall, the energy is the same, it's more stable.
So the promotion step, though, costs energy. So why do they hybridize? They hybridize because they need to, right? Because you have these electrons that need to point in 4 different directions, don't you? And so they are interfering with each other. Well, what happens if if all of a sudden a fight breaks out between the different groups here? Okay? Okay, you're separated and I need to separate you. What if I have a bigger space? What if we're out in a concert hall? You guys gonna have interactions? I put you each at a corner of a concert hall. No, you don't have to be separated, do you? We don't have to make more effort to do that because we have the extra space, right? And so when you have a very large central atom, anything period 3 and below, what actually ends up happening is you have a lot of space. And so you no longer have to hybridize for these electrons to fit around there because the center is just so large, right? And that's that same polarizability, that same trend that we've seen on all these other things where it's polarizability, the space around it, the angles, etc. These are all the same trend. Okay? The central atom's large enough that you just don't need to take up the extra space. You don't need to hybridize. And so the H2S atom, the S atom's much larger than the oxygen, plenty of room. Your bond pair repulsions, your hydrogen ligands, is far less important and doesn't drive the geometry like the others do. Okay, like the H2O. Now we do need some rules. These are Drago's rules, actually. They are entirely empirical, no math. Okay, and which is nice, right? And so these are how you tell if you're going to have to hybridize or not. Okay, they have to fulfill all of these 4 criteria for you to not need to hybridize. So the sum of the sigma and bonds and the lone pairs on the central atom is 4. Okay, you have to have 4 more to need to hybridize. You have to have 4. The central atom contains at least 1 lone pair. The electronegativity of the ligands is less than or equal to 2.5, and the central atom is from the 3rd period or higher. So notice, for example, sulfur fulfills all of those. And so we do not need to hybridize, right? Okay. By the way, this electronegativity right here, if you start looking at this periodic table and electronegativities, you notice that basically everything in period 2 and 1, there's like half the things are higher than 2.5, right? And then you look here, again, period 3 and higher. So everything on period 3 could possibly fulfill this, but we get things that hybridize yet if we start looking at things like chloride, right? Like we can get hybridization with those. Okay. Okay, let's talk about Bent's rule. So Bent's rule specifically is the atomic S character concentrates in orbitals directed at the more electropositive substituents. So for example, the hydrogens, we had been looking at the hydrogens. They are, what's electropositive mean, by the way? So electronegative meant what?
How much it wants an electron?
Yeah, how much it pulls electrons to it, right? Okay. And what's electropositive then mean? Yeah, or how weakly it pulls electrons, right? One of the two. Okay. Okay, so what did we notice about lone pairs in terms of S character versus hydrogens? The lone pairs had more S character, right? See that? More S character, right? Because they're more electropositive, right? Another way of saying this is the more electronegative thing is going to have less S character, right? Okay. Is that making sense? Okay. Okay. And remember, this is the other side of that bond that we're talking about. By the way, if you have a lone pair, that's about as electropositive as you're going to get, right? It's going to be repelling the electrons the most. Okay, so a corollary, of course, the opposite of this is also true. Electronegative ligands are going to prefer occupying higher hybrid orbitals that will be more p character, higher percentage p character. Do you guys need an example of that, or are you good? Okay, let's talk about CH3Cl. Okay. And so if we look at CH3Cl, there's 2 ways of looking at this that would actually give us opposite answers. Okay, there's the steric argument, and so we would predict the ClCH bond around that to be 109.5, and that's the Cl atom is going to be larger, and so we'd push the H atoms away from it, and because it's a larger atom, right? It's a bigger thing, the other things get pushed down. Okay. The other way we could look at it is from the Vesper argument. So again, that would predict that the HCH bond angle is going to be larger than 109.5, and this is going to be because these bonds are shorter, and so the electrons lie closer to the middle atom, and so should push each other away more, right? Okay. Those are opposites. So which one is true, or which one is going to hold more true in this case? Okay. Which one's going to be the major contributor? So we can actually use Bent's rule for this. So because the Cl is more electronegative ligand, it's going to prefer a hybrid orbital that have greater p character. And so they're going to have more p character, less s character. The sp3 hybrid bond angles are 109.5. If we go to sp2, that's 120. Sp is 180. What does that tell you about the bond angles that involve less p character? They get larger, don't they? Yeah. So p character tends to shrink the bond angles. You already knew that actually from the previous formula. That previous formula told you the same thing. Okay. So the greater p character is going to imply a smaller bond angle, and so the Bent's rule predicts your ClCH bond angle would be less than 109.5. That's going to be the smaller one. The HCH bond angles are going to be the larger ones. Notice that actually lines up with the this one down here. And in fact, if we look at the experimental bond angles, what we'll see is ClCH bond angle is actually 108 degrees. So that's actually less than 109.5, like we would predict for Bent's rule. Okay, and I guess I'm over time, aren't I? All right, I guess I'll start from here next time. You all have a wonderful day. First lecture back from spring break, huh? Yeah. All right.